Conducting a hypothesis test with two samples and two means, looking at the difference between the means, is really not that different than conducting the hypothesis test with a single sample and a single mean. The main difference is that our null hypothesis is going to be that the difference between the two population means equals some value d sub 0. We don't make a hypothesis about what the mean will be for each of the two populations represented by the samples. Now, in the single sample case, we used the central limit theorem to compute our z-values to do our hypothesis test. That's the same here. So we need to know the variance for both populations, and our sample sizes need to be at least 30 so that we can invoke that central limit theorem. So when we do so, we just simply substitute d sub 0 in place of the difference of the two population means when computing our z-values. And we compute the hypothesis test, we conduct the hypothesis test the same way that we did for the single sample. So here are those two things that are a little bit different. My null hypothesis is given there, and then the way that I compute my z-value to conduct my hypothesis test with the two samples and two means. Now, another thing that we might be interested in is how we choose a sample size so that our test has a certain power. So the power of a hypothesis test is computed by taking 1 minus beta. Now remember, beta is the probability of a type 2 error. And for the type 2 error, we couldn't do that unless we picked a specific value for the mean to fall in our alternative hypothesis range of values. So in order to do stuff with this, we need to consider the true mean and our hypothesized mean with our null hypothesis. Now the difference between those two is delta. So delta is going to equal the true mean of the population minus the mean that we hypothesized it to be with our null hypothesis. So when we have a single tail, a one-tailed test, and a single mean that we're looking at, then what we do to find the sample size that we need to have the certain power test is we take our z sub alpha plus our z sub beta values, we add them together and square them, and then we multiply them times the variance of the population, and we divide by the difference of the true mean minus our hypothesized mean squared. Now, when we have two samples and we're looking at two populations, looking at the difference between two means, we can do the same thing. Z sub alpha, Z sub beta, those values, we can find them the same way. The only difference is we'll now multiply times the sum of the variance of each of the populations that we're looking at. And then again, we're going to divide by delta squared. Now, you might be saying delta doesn't make sense that way, and it doesn't. When we have two means that we're comparing the difference of, delta is actually going to be the difference between the difference we hypothesized and the true difference. So delta is always the difference between the true value and the value that we hypothesized. Right? In the two sample test, it's identical except for we know that we need to take the alpha, the significance level, and we're going to break it into the two different tails. So we'll be splitting it in half to create that critical region. So instead of having z sub alpha, we'll have z sub alpha divided by 2 for each of our sample size approximations. So that's how we can find our sample sizes for our hypothesis test to have a certain power in the one-tailed, two-tailed cases with just a single sample, single population, and with two populations where we're looking at difference in means. Now, it's also really helpful to be able to think about and look at the difference in means between two populations graphically. So I wanted to just remind you that box plots exist. So we did box plots way back at the beginning. You've done them other times in life. Box plots are a really great way for us to be able to compare two means.